Hi, this is Elliot Fishman, and welcome back to part 2 of the earlier detection of pancreatic cancer and the role of AI and radiomics. We left off last time with this image showing you our training of the computer to be able to recognize the pancreas and various organs. One of the key things, of course, in order to be able to use AI is the computer needs to learn what the pancreas looks like. And here we've trained it, and it's very important, particularly when you want to look at accuracy with radiomics or classic AI, to do exactly the pancreas, no more and no less. And you can see from these images, the computer can find the pancreas, and then you could train the computer to be able to recognize the tumor in the pancreas, as you can see in red. So a combination of detection of the gland and then analysis of the tumor. And then looking at the pancreatic duct, we talk about how duct cutoff is so important. We need to train the computer to look at the duct. And we're doing that work with radiomics and with AI and looking inside the duct, trying to pick up early tumors. All of this becomes very important. In this article by Kawamoto, development of algorithms using deep learning to detect the pancreas and PDAC is dependent on the quality of data input, and therefore it's important to have high quality data. And we know that's always going to be the case. So you need to make certain you have good protocols. Kawamoto goes on to say, in conclusion, a study found that segmentation of the pancreas using deep neural networks is accurate and can be applied for AI-based volumetric analysis in the majority of cases, which is indeed very, very important. In this article by Matre and Topol, talking about current guidance for pancreatic cancer is restricted to high-risk patients. Those are the patients who have family histories of pancreatic cancer, but it's a small group, like 25,000 patients over many years. And yes, you could pick up a couple of cancers earlier at an earlier stage, but again, it's limited in how many patients are being taken care of. When we speak about AI and developing algorithms, we need to look at the 85% of the cases that are not related to genetic changes. We need to find all of the cancers. Again, this article goes on to talk about the individuals at sporadic risk who are identified through the mining of EHR data. And again, the importance of looking at imaging and then things that will be developed, whether it's liquid biopsy is one good example, where a combination of liquid biopsy and AI for imaging and LLMs for analyzing the patient's chart and looking for risk factors, including diabetes, are all going to be very, very important. In this article by Moglia, just recently published, talking about pancreatic segmentation being very difficult. Again, we've done a lot of work with segmentation. We have people who segment the cases. That's very expensive. It takes nearly an hour a case. How do you do things better? People have done select cases with some reasonable results, but the question is, how do you do all the cases all of the time? Limited availability of experts, human error, and scalability issues further complicate the process. Extensive training requirements and reproducibility concerns hinder the widespread adoption of manual segmentation methods. You know, our hospitals like yours, we don't have enough techs, we don't have enough radiologists, we don't have anyone to segment the gland. And if you tell me you want to do it on all cases, it's just unreasonable. From a deep learning perspective, the learning-based models for segmentation face several challenges. And again, we can look at the problem. Supervised learning models need pixel-level annotations. A common problem for semi-supervised learning is the violation of the same statistic distribution for both labeled and unlabeled data. Third, for self-learning, designing pretext tasks for medical imaging can be challenging. On the other hand, contrastive learning requires relatively large unlabeled data sets, which are difficult to obtain and maintain due to patient privacy. So again, we're talking about problems. They showed some work they did where you can see the pancreas identified. The red is where the patient's pancreatic tumor is. So you can see a reasonable attempt at localizing the gland, localizing the duct, and this becomes very important. You need to do this, and again, you need to be able to do it on the normal cases as well. Radiomics is dependent on accurate data, and so is AI. So we need to do better. So one of the things we worked on with Microsoft is looking at being able to find the gland. And what we did is we trained the computer and we looked at how well the computer did compared to experts. We had 4 experts. Now, one of the things you recognize, even experts will vary. It's hard to be exact. Even when you look like it's perfect, it still will vary from person to person. And these are patients, or these are people with lots of experience. When you look at the DICE score versus the modeling, you could see that in better than 95% of cases, the computer was equal to a radiologist or a trained technologist. Certain cases were difficult: low abdominal fat, fatty infiltration causing decreased attenuation, and local inflammation can create problems. But the cases where the computer has problems are also the cases where radiologists have problems. So one of the things we know is the computer needs to be able to tell you, hey, I have a problem on this case, and then the radiologist can help the computer be more accurate. So again, model performance approached human performance. Evaluating in multiple human annotators is more realistic than using model benchmarks. So we're able now, using the computer, to be able to isolate the pancreas essentially as good as a radiologist. And as I highlighted before, improved segmentation is critical if you want to look at the patient's radiomics. That radiomics performance increases with increased robustness of the data set. And we think about how we want to do things as basically a pipeline for radiomics feature extraction. This pipeline will not work unless you can isolate the pancreatic gland accurately. You can't cut off any of the pancreas, and you can't take additional material from stomach, from spleen, from duodenum or aorta, or anything else. So again, we need to put all of this together, and we're working on it. Now, one of the things, of course, to think about is not only when you think about early detection of pancreatic cancer, but you think about cystic lesions, right? Because one of the risks for pancreatic cancer is IPMNs. Now, only about 3% of IPMs will become malignant over the patient's lifetime, but there's increased risk. And you know, your practice like ours, we seem to be scanning a zillion patients with CT or MR for pancreatic cysts. And again, how do we get around that? How do we learn to manage that? Well, one of the challenges has been, if you look at this article, there was a multi-center, multi-site study. 840 patients went to surgery because they had cystic pancreatic lesions that the GI folks and or the surgical folks felt was suspicious for malignancy. Yet in only 40% of the cases did the patients actually have malignancy or high-grade dysplasia, which means that 60% of patients had surgery. Surgery is a Whipple's or a distal pancreatectomy. In the best of hands, there's still a 1 to 2% mortality, and complications, whether it's dietary or lifestyle, is not inconsequential in another 10 to 20% of cases. Well, Bert Vogelstein did a study taking that data and developing what's called the ComCyst, being able to do better than the clinicians and will correct in 60% of cases. Now, 60% is not great, but it's a lot better than 40%. What we then did with Microsoft at the suggestion of Bert Vogelstein about 3 years later is reanalyze the data set with the newest AI algorithms. We did not reinterpret the CTs. We did not have more lab values. We had the exact data from the initial study that Vogelstein group looked at and went from 40 to 60%. What we were able to then do is go forward and relook and restudy the data. And it's published in this article. Juan Ferez, who's an amazing human being, but he's also the head of AI for the AI for Good at Microsoft, was the key author and lead person on this project, talking about how with pancreatic cysts, what do we do? Again, most of them are benign. How do you decide who to manage? Well, using explainable boosting machines, which have been used for things like heart disease and breast cancer and telecommunications and credit card fraud. What it does, EBMs do, is you can see exactly how the program is going, why the computer is making select decisions. And it works very well for medical. An important thing is we don't look at the probability of a population having cancer or having a select finding. We look at the individuals. So in other words, when I'm looking at a patient and you have a cystic lesion, the computer can say, hey, look, this is 95% a benign lesion, or it's 90% malignant. This helps both the clinician as well as the patient make the correct decisions. And so it's very important, this idea of probabilities. Now, the other thing with EBMs, you can look at all of the information that was available when we studied the patient, and it shows you what predictors were used. Interestingly, the predictors that we used were different than what clinicians use, and that explains why the accuracy was over 90%. Here's just one example of a single patient where current management, and what happened was the patient went to surgery. We would have said discharge the patient or monitor the patient. It would not have been surgery, under 15%. So again, all of that information led to a better diagnosis. And so most importantly, when you look at EBM, the Microsoft algorithm, compared to current standard of care, it was significantly different on predicting surgery, predicting who to monitor, and predicting discharge. The most important single thing was 92 surgeries, or a 59% reduction in surgeries would have happened. We would have followed less patients. Everything got better, but especially the surgery part. Avoiding unnecessary surgery is everything we try to do. And in total, in this cohort of patients, the use of EBM changed management in over 25% of patients. Now, we are doing another group of patients with the University of Pittsburgh and Anne-Marie Lennon of 8,000 patients to see if these algorithms continue to work, but it's indeed very exciting. So EBM had greater sensitivity and specificity for identifying the correct management compared with either clinical management or previous AI models. Indeed, very, very exciting. When you look at the future of pancreatic imaging and staging, we need to have better scan protocols, but we've worked on that. We mentioned cinematic rendering. We've now spoken about AI. We've now spoken about radiomics. And again, in this article by Gonda talking about pancreatic cysts and how to manage them, the article was excellent in making the point that we're just not that good. If you look at many of the cysts, serous cystadenomas, 0% chance of malignancy, IPM typically 1 to 3%. We need to get better. Too many patients are going to surgery. Too many patients are being followed. What else can we do? And again, in this article by Wang, making the point that identifying pancreatic cancer early can be complicated by inherent tumor characteristics or concurrent pathologies that might distract the radiologist's attention. The biologic understanding of the chronologic order of early pancreatic cancer imaging is still evolving. Retrospective studies of serial pre-diagnostic CT exams have shed some light on the key imaging findings of early pancreatic cancer. So we are making progress, but we have a way to go. We know, and in a sense, this gives us lots of hope. Localized steatosis can occur 1.6 years before the diagnosis of pancreatic cancer. We know that main duct abnormality, I showed you an example at the start of this talk, such as cutoff or dilatation without a discrete mass, may present up to 1.1 years before diagnosis. So we know there are signs. Before we used to think that pancreatic cancer, today you're normal, tomorrow you have cancer. Well, now we're understanding, not surprisingly, that cancer may be 1 to 3 years there before we diagnose it, which means if we can do better with imaging, we can save many patients' lives. So now what you need to do is saying, okay, we can find the pancreatic gland. We can use radiomics. In select cases, we'll do cinematic rendering, but typically not in those early cases. We're not sure how well it works, but something to look into. But what about AI? Well, here what we're working on now is a multitask model that combines local segmentation using voxel cross-entropy loss with a global classification head that captures secondary cues in the gland, the pancreatic duct, and bile duct. Our model can aggregate local and global information for more accurate tumor detection. Also, our model provides a set of classification probabilities as it analyzes each lesion. This is the newest work with Microsoft's team, the ability to pick up small cancers. We haven't published this yet, we're about to, but the accuracy for picking up tumors 2 centimeters or less is in the mid-90s. Our accuracy is better than any of the published data. And we also did not just look at pancreatic cancer and normal, we looked at multiple different tumors. And you can see in this case, there was no discrete mass, or barely a discrete mass, but there was a big duct. And when the computer analyzed everything, it said that 95%, 0.959, is that it's a cancer, and only 0.02 is a normal. This patient will get biopsy, will get surgery. Again, you can see that it wasn't just saying we see something, but we see something and we know beyond a shadow of a doubt it's pancreatic cancer. And when you look at our accuracy, and I won't go through the chart in detail, but again, better than 90% accuracy in picking up small pancreatic cancers. Now, a number of articles, again, and I'll end with a few different things. This article by Topol making the point that AI, again, mining of electronic health records, can add to the information we get from imaging. The combination of AI does not stop at the initial EHR-based enrichment steps, since deep learning models are also being developed to improve the resolution of CT and MR for detection of early subsonometer cancers. We talk about some of the work from NVIDIA, Kimberly Powell, when she spoke last year, making the point how we process our tasks, especially those that are multimodal, will benefit most, particularly in complex collaborative environments like tumor boards. AI integration is becoming tangible. It is tangible and it's critical. Generative AI, which you read about every day, can analyze vast amounts of patient data and look for key factors that'll help you understand the risk of specific patients. In the future, many of us will find that our professional success depends on our ability to elicit the best possible output from large language models like ChatGPT and to learn and grow along with them. This becomes very, very important. Now, can AI do better than the radiologist? Someday it's true. I think for the foreseeable future, you're going to have AI assisting the radiologist. Remember, we've said before, do not resist AI. Embrace AI, but have it work with you. And hopefully together, the radiologist and AI will do best for our patients. Now, the future of AI, no one can predict the future. We wrote this article a few months ago. In the long term, we have to wait and see what happens. But in a sense, we know what's happening because we can see the changes AI is going to bring. Topol talks about AI-enabled medical scan interpretation. Machine digital eyes can glean from more information from a scan than human experts can detect or accurately decipher. It may not be long before a chest X-ray report comes back with your risk of heart attack and stroke over the next decade, your calcium score, cardiac ejection, fracture, presence of a leaky valve, and whether you have type 2 diabetes. Now, Topol is a cardiologist, which is why he probably picks all of those examples, but he's indeed very correct. A prodigious amount of medical information is currently not being harnessed, much of which could be informative to patients and reduce the cost of additional medical imaging and misdiagnosis. Again, we're sitting at the start of the greatest opportunity in mankind's history for being better able to detect things. Matt Lundgren, who is at Microsoft, the bottom line is this technology is going to change the world, including every aspect of healthcare, and the capabilities that have been arising and the rate at which people are adopting these new technologies are astounding. Matt's incredible. He is a radiologist, or was a radiologist at Stanford, and now he's working with Microsoft. So he's one of those people who kind of is sitting at the crux between clinical and research and AI, and his work is really indeed very impressive. This idea about a model ecosystem, how we need to do things, how we need to change things, is something that we read about every day and we need to get involved with. Rajapur makes the point, although many current radiologic AI applications are designed for radiologists, there's a small but emerging trend globally toward the use of medical imaging AI for non-radiologist clinicians as well. So not only are we going to be using AI, but the surgeons, the GI folks, the internists, everyone's going to be using AI. And the combination of AI and liquid biopsy, how we work is all going to change. How pathology and radiology work together, they're going to have to work even closer together. With the introduction of AI algorithms, provided that data management and safety regulations are in place, is reduce the cost and time needed to diagnose the disease. I think that's what's very exciting. Remember, with pancreatic cancer, typically the earlier we diagnose, the earlier the stage. The earlier the stage, the better the outcome. And again, AI's threat to the medical profession, while authors of literature are fighting for regulations to control the use of AI in art, physicians should contemplate how to take advantage of the potential benefits from AI without losing control over their profession. Again, it's important for us to be at the front, not at the back. This article by Rajapur also makes the point, again, the emerging perspective suggests that a clearly defined division of labor where AI and radiologists assume separate responsibilities in the diagnostic process might provide more reliable results. And what that means, perhaps AI will read plain chest x-ray by itself, or at least the normals, and then kick out the abnormals for the radiologist to read. I don't see AI alone looking at the pancreas, but I see it doing it with the radiologist. And perhaps there's some things where radiologists will do it without AI at all. So this role separation is something that's going to evolve, but we'll see what's happening. There was an excellent article you need to read, Translating Artificial Intelligence Breakthroughs into Cancer Diagnosis. Juan Ferez, who I mentioned before, is the head of AI for Good at Microsoft. Ed Catmull, who was the founder of Pixar. Bert Vogelstein, who is the chief scientist and discoverer of many of the key things affecting our genetics. And Joshua Vogelstein, who's a computer science and researcher and Bert's son, wrote this article, and I'll leave you with a final quote. Every week, numerous articles are published that showcase the potential of AI and machine learning to revolutionize medical diagnostics. These studies often report impressive results, yet a significant gap persists between these conceptual and theoretical advances and the practical deployment of AI ML in clinical settings. This disconnect raises critical questions about why AI and machine learning tools, despite their promise, have yet to become commonplace in oncology. Excellent point. Juan's point is well taken. The next step is bench to bedside. We have lots of opportunity. It's going to take a little bit of time, but we can't just worry about writing articles and then stopping there. We need to change the world, and hopefully we will. And with that, thank you for your attention. Catch you later, guys. Bye. If you like this video, make sure to subscribe to the CTisus YouTube channel. You can also visit us at ctisus.com for even more videos, plus quizzes, pearls, protocols, and oh so much more. We're also in the App Store and have well over a dozen apps for iPhone and iPad, all completely free. Thanks for watching.